Hello.
Sir.
Good evening.
Good evening.
Ramakant sir, good evening. Hello. Venkateshwara sir. Hello. హలో రమాకాంత్ సార్.
Yes, sir.
ఇది ఎవరిది ఇది డిపార్ట్మెంట్ ఆఫ్ అని ఉన్నది?
Nagaraj, sir.
నాగరాజ్ సార్ స్టార్ట్ చేసిన.
Ah,
ఇది అందరికి అడ్మిట్ అని వస్తుంది.
అదే.
అదొక్కసారి యూట్యూబ్ లింక్
ఇస్తున్నా, sir.
ఒక్కసారి పంపించు. వెంకటేశ్వరరావు సార్. హలో. రమాకాంత్ సార్. నాగరాజ్ సార్.
సార్ చెప్పండి.
సార్ ఇది సారీ 2 డివైజెస్ ఉన్నట్టున్నాయి కదా, దేనికి వల్ల ఒకసారి అడిగి ఇవ్వండి కో హోస్ట్.
ఓకే.
Sir,
Madam.
shall we start?
Madam, you start the program.
Yes. Good evening, everyone. A warm welcome you all for the last day International FDP on Data Science, the New and Future Technology. So before inviting our today's resource person, Dr. Venkateshwara Rao, I feel it an honor to introduce you, sir. Sir is an assistant professor at NIT Warangal in the Department of Computer Science and Engineering. He obtained PhD from University of Hyderabad. His research interests are in data mining, machine learning, with a specific focus on machine learning techniques for recommended systems. His research works have been published in various reputed journals and conferences proceedings such as patent recognition letters, information services, expert systems with applications, journals of approximate reasoning, etc. Sir has also delivered various guest lectures in several international and national workshops at IIT Hyderabad, Central University of Rajasthan, etc. Now I hand over the session to Venkateshwar Rao, sir. Over to you, sir.
Thank you very much, Jayashree, madam, for your kind introduction.
Thank you, sir.
Am I audible?
Yes, sir.
All right. Give me a second. It is taking time to go to full screen mode.
Yes, sir. Yes, sir.
Yeah. Thank you very much. Is the screen visible?
Yes, sir.
All right. Good evening, everyone. In today's session, we are going to discuss, we're going to introduce deep learning and then discuss about the neural network basics. How much time do I have for this, madam?
Sir, up to 6:30, sir.
Okay, all right. Okay.
Yeah, okay.
So in today's session, we are going to discuss introduction to deep learning and neural network basics. This is the outline of my talk. We'll discuss first AI versus machine learning versus deep learning. Then we'll introduce the deep learning and applications of deep learning. Then we'll start the neural network basics, in which we'll have to cover few machine learning basics to understand the neural network basics. Then we'll discuss what are shallow neural networks, what are deep neural networks, forward propagation and backward propagation. So this is the overview of talk. All right, so what is the difference between artificial intelligence, machine learning, and deep learning? I'm sure you might have heard of all these words because AI Burge has created enough awareness of different areas like machine learning, deep learning, isn't it? So though you're not fully aware of it, I'm sure you've heard of it, isn't it? So what is artificial intelligence, machine learning, and deep learning? Artificial intelligence was initiated with an intention of creating human-like intelligence, isn't it? So to develop programs, to perform tasks that typically requires human intelligence, right? So one of the aspects of the human intelligence is that we have the ability to learn things from our experience, isn't it? So machine learning has a set of algorithms that has the ability to learn without being explicitly programmed, right? And in deep learning is a subset of machine learning in which the artificial neural networks adopt to learn from vast amounts of data. So artificial intelligence is to mimic the human intelligence, in which we have subset of algorithms that has the ability to learn without being explicitly programmed, that we are calling as a machine learning. So there are various algorithms in machine learning like SVMs, decision trees, linear regression, logistic regression, all these different KNN. different algorithms. Out of this, neural network is also one of the subset of these algorithms. So subset of machine learning algorithms in which artificial neural networks adopts to learn from vast amounts of data. Right. So this is the difference between the artificial intelligence, machine learning, and deep learning. So what is the actual difference between the traditional machine learning algorithms versus the deep learning? So in case of traditional machine learning algorithms or models, they work with the handcrafted features and relatively simple trainable classifiers. So you have to explicitly extract the features from the data, the raw data that is given to you. So if you extract features from the image, so given an image, you extract a d-dimensional feature vector from the image, right? So you have to explicitly extract the features in case of machine learning algorithm. Once you extract the features, you pass it to the training classifier, right? So once you train the classifier, it will give you the output. So it will give you the hypothesis will give you the output, right? So what are the limitations of this traditional machine learning algorithms? It is very tedious and costly to develop handcrafted features, right? So you should have a domain knowledge for that to extract the features from what features are helpful, what features are not helpful. To understand all this, you require some domain knowledge to understand that. And the handcrafted features are usually highly depend on one application. So it may vary from application to application. Right. So if you're classifying indoor or outdoor, you may have a different set of features. If you're classifying it as whether it is um, uh, to detect an object, it is a different set of features. So all these different applications have different set of features. The same features may not work in different applications. So that's what I'm trying to say. So this is traditional machine learning algorithm. In deep learning has inbuilt automatic multi-stage feature learning process. You need not explicitly extract the features in case of deep learning. It automatically extracts these features in case of deep learning. So, and learns rich hierarchical representation of these features. For example, at low level, it may just have a pixels and then edges, and then as you proceed to the higher levels, maybe some motif you can get, or you can get parts of the image. So these are the different features that we get automatically from the deep learning framework as we proceed towards the deeper layers in the network. So if you take image, the lower level representations could be pixels, edges, and middle level representations could be texture, motif. Higher level representations could be part, object, like that. If you take text as an input, lower level features could be character, word, and middle level features could be word, group, classes, and higher level representations could be sentences, story, something like that. So it automatically learns this hierarchical representation of the features from the raw data automatically. So each module in deep learning transforms its input representation into a higher level one in a way similar to the human cortex. The same thing happens in the case of human cortex also. The few applications we'll see to get some motivation. So automatic colorization of black and white images. Given black and white images, it automatically converts. It automatically colorizes the images. And videos similarly. Optimizing images like post-processing of features like optimizing color curves and details, optimizing the illumination like this, and optimizing color tones like warmness, and captioning an image. Given an image, captioning that image, like if you see given that image, you can give a caption like person riding a motorcycle on a dirt road. And similarly, object detection in a photograph. As you can see in the figure, there are three objects that are detected in the photograph: dog, horse, and person. Prediction of a next word. This you might have seen in the Google also. When you type something, it predicts the next word, isn't it? Automatic machine translation, translating from one language to another language. There are various other applications that are not listed out here. So now the question is, why is everyone talking about deep learning? Deep learning, the neural network is there since 1960s. But why is that everyone talking about neural network now? And one more thing is that since 1918, there are not much changes happened to this neural networks. right? So, but then now it has come into the light because now we have a faster computers um, that can execute this neural network frameworks, and now we have a different nonlinear functions are introduced into this neural networks like ReLUs, and now we have better optimization techniques and more hidden units. Because of this faster computation of this, we can venture to have more hidden units like larger networks. And in addition to that, it has won numerous pattern recognition competitions. Once it is working on different problems, everybody shows interest to learn that, right? Or apply that in your domain, isn't it? So it also requires minimal feature engineering, unlike in case of machine learning algorithms. So these are all made the deep learning into limelight. And another reason is that because a lot of money has been invested in this, right? I'm just avoiding this to save time. So if you compare the traditional machine learning algorithms and the deep learning algorithms in terms of their performance and the size of the data, as you can see in the figure, as the size of the data increases, the traditional machine learning algorithms reaches to some saturation level after some size of the data, right? Whereas if you see the deep learning algorithms, as you increase the size of the data, the performance of these deep learning algorithms are increasing, right? Is increasing, right? So there are different paradigms in this deep learning. Like in supervised learning, we have feed-forward neural network, convolutional neural network, sequence modeling. I mean RNN and its extensions. And similarly, in unsupervised encoder-decoder architecture, and similarly in unsupervised learning, we have autoencoders, generative adversarial networks, and in reinforcement learning also we have some models. Right? So there are different paradigms in this deep learning classified into supervised, unsupervised, and reinforcement learnings. And if you see this feed-forward neural network or any other framework that is there in this slide, there are two things that you can observe here, two main things that you can observe here, encoder and decoder. Right. So at high level, neural networks are either encoders or decoders or combination of both. Right. So what is encoder? Encoder finds the patterns in raw data to form compact and useful representations. So, so it is trying to find patterns in the raw data to form compact and useful representations. Right. Wait, one second. Okay. So, and then once we get this compact representation of the raw data that we have at hand, we can pass it to the decoder, or we can use this compact representation for the prediction. There's two ways that you can use this compact representation that you have got it from the encoder. Either you can decode this, the compact representation, and generate some high resolution data from this compact representation, or you can directly use this compact representation for the prediction. Right, there are two ways that you can use. So the generated data by the decoder is either new example or descriptive knowledge. Right. So in case of feed-forward neural networks, the first one, data passes from input to the output in a single pass without any state memory of what came before. So most of the networks in deep learning are feed-forward neural network. But generally, when somebody says feed-forward neural network, usually they refers to multi-layer perceptron, but not the other feed-forward neural networks that we have in deep learning. Okay, so usually people refers to multi-layer perceptron when somebody says feed-forward neural networks. So in case of convolutional network, these convolutional neural networks has the spatial invariance trick to efficiently learn local patterns. When I say spatial invariance, it means that irrespective of the location in which the feature present, it could extract that. So for example, you would like to extract the bird beak or a cat ear. So irrespective of the position in which it is there in the image, either it is in the top left corner or it is in the bottom right corner, irrespective of wherever it is, right? It has the same meaning. So convolutional neural network has spatial invariance property. Recurrent neural networks are the networks that have the cycles, and therefore a state memory can be unrolled in time to become feed-forward neural network. So you have to unroll this to make this feed-forward neural network. It has to unroll in time, right? So it shares parameters across time, whereas CNN shares parameters across space. Like, so encoder decoder architecture next. So instead of making predictions, if you observe, first three are making prediction. The fourth one is not making prediction. Instead of making prediction, encoder decoder architecture generates a high resolution, high dimensional output using decoder by unsampling the compressed representation. Right. So if you see, the encoder can be any encoder, decoder can be any decoder. It means that you can give input as an image and you can apply a CNN encoder there, and you can get the output as a text. You can apply RNN decoder there, right? So encoder could be different, decoder could be different. You need not use the same kind of encoder and decoder. So encoder converts this raw data to some compact representation. From that compact representation, you decode that and get some output, right? So the applications of this encoder decoder includes image captioning, machine translation, and many other. So few applications I'm listing out. Then comes to this autoencoder. Autoencoders is one of the simplest forms of unsupervised learning. So to generate an exact copy of an input data. So if you see here, the output is the exact copy of the input, right? So it means that you need not spend efforts to label the data, because the label is exact copy of the input, right? So but then why we have to learn the exact copy of the input? If you see, the focus here is on the representation but not the input, I mean the output, right? So here we are trying to learn the compact representation of the input, and this compact representation would be useful for the other applications, right? So in the process of generating the exact copy, you are learning high quality representation in between, which is very uh, less in size as compared to the input, and which forms the basis for this generative models. So generative models generate new realistic samples from a particular representation. Generative adversarial network, they generate new samples from a particular representation, right? So in simplest form, the training process involves two networks. One network called the generator, as you can see in the figure, and other network is the discriminator. So the task of generator is to generate a data instance and trying to fool the other network. This is the other network, the discriminator network. So it generates some data and tries to fool this network, that is discriminator network. And the discriminator classifies the images as real or fake images, right? Reinforcement learning. Reinforcement learning is a framework for teaching an agent how to act in the world in a way that maximizes the reward. So you act, you take the reward. So you have to, agent has to act in such a way that maximizes the reward. Like for example, in a games, what do? You take one step. This step may give you reward, or it may you may lose some points, right? So the agent here has to act in such a way that it maximizes the reward. Now, similar is here also in case of reinforcement learning. So when the learning is done by the neural network, we refer to it as a deep reinforcement learning. If this learning is by any algorithm, then any other machine learning algorithm, we just call it as a reinforcement learning. If the learning is by neural network, we refer to it as a deep reinforcement learning. As if you have any queries, you can interrupt me. What happened to my slide? Okay. So more precisely, deep learning is a branch of machine learning where neural networks learn from large amount of data. So what is neural network? We've been talking about this, right? So we have been talking about this from long time, since the beginning of the session. What is neural network? So we'll discuss artificial neural network basics. So what are artificial neural networks? So artificial neural network is an interconnected group of nodes inspired by simplification of neurons in the brain. So the original goal here is to mimic the human brain, right? But the current attention is on performing specific tasks like classification, regression, different object detection, different tasks. Okay, and used on variety of tasks like in computer vision, speech recognition, machine translation, social network filtering, and various other tasks and applications. So if you see this, human brain has around 80 millions to 1000 billions performing 1000 billions of neurons performing various functionalities depending on the where they are located in the brain. So say particular set of particular part of the brain may be controlling the vision, some part of the brain is involved in interpreting the pain and touch, and some part controls the speech, smell recognition, and so forth. But irrespective of the location where this neuron is present, these neurons have some common structure. So we are trying to look at that common structure from the biological neuron and try to model a similar thing in an artificial neural network, that is artificial neuron. Okay, so the neurons in the human brain, yes. I'm getting some noise. Do you have some question?
No, sir, you can continue.
Okay. So the human brain have, many neurons, 1000 billions of neurons, and depending on the part where it is located, they have different functionalities. But irrespective of the location where it is present, these neurons have some common structure, right? So if you see this biological neuron, as you can see in the figure, there are 4 main parts in each neuron, like. So the main 4 main parts are dendroids, soma, axon, synapses. So the task of the dendroids, they receive spiking signals from other neurons. So they receive inputs from the other neurons, and width of this dendroid determines the weight associated with it. So if the width is more, then you give more weightage to that particular dendroid, right? And soma, it receives the spiking signals from the dendroids, integrates them. If the resultant signal voltage is greater than certain threshold, then send that signal through axon, right? So it is receiving the signal from the dendroid, integrating them. If the resulting signal's strength is greater than certain threshold, then it passes that signal through axon to the axon, right? What axon does is it propagates the spiking signals generated by soma to other neurons and connect to other neurons through synapses. As you can see, it passes the signals to other neurons through synapses. What are synapses? Synapses here act as a memory organ in the brain. It connects the axon of past neuron to the dendroid of the next neuron. So it acts as a connection between the dendroid of the previous neuron and the axon, between the axon of the previous neuron and the dendroid of the next neuron. So the biological neuron has this structure. So if you see the artificial neuron that is developed from this biological neuron also has the similar structure. It has the inputs, it has the dendroid-like structures here, those are called the inputs, and soma-like structure, that is the linear combination plus the heart limiter, where you are setting up a threshold If it exceeds, you will pass through the output to the axon, right? So we have a similar structure here also, right? To take a decision of whether it is +1 or minus, I mean, if it is greater than threshold, then it is +1. If it is less than threshold, then you may pass the -1 here. So what is this? Is an artificial neuron, one single neuron, right? What is neural network? The collection of neurons, isn't it? So input of one neuron is passed as an input of the next neuron, okay, layer by layer. And what are they used for? This slide I basically kept to maintain the continuity to the next slide. It is used for various other tasks that are not listed out here also. So it can be used for regression, classification, noise reduction, prediction, and various other tasks. So if you see the supervised learning problem, these are the machine learning basics that I'm discussing and which are necessary for the, I'm only touching the things that are necessary for the, to understand the neural networks. Like, so in a supervised learning problem, as you all aware probably, so what we are trying to do is that we have given a training set of pairs, like xi, yi, right? x1, y1, x2, y2, xn, yn. What is this xi? Is a feature vector. What is yi? Is a target variable. So in case of classification problem, if you see, it is the xi is the feature vector and yi is the class label. In case of regression problem, if you see, xi is a feature vector, yi is a some continuous target variable. Correct. So if the output variable is continuous, then we call it as a regression problem. If the output variable is discrete, then we call it as a classification problem. So for example, if you want to predict housing prices based on size in square feet, so the size in square feet here is a feature, okay, single feature we took for the simplicity. So size in feet here is a feature and price in dollars is a target variable. Because price is a continuous variable, we call this as a regression problem. So given this data, given a new house wherein we only know the size in square feet, we will have to predict the price of the house in dollars.
Sir, I'm having one question that here for optimization process, we have solved that we are using matrix processor, logical processor.
I am sorry, but your doubt is not clear to me.
Hello?
Yes, I'm sorry, but your doubt is not clear to me.
Hello?
Yes, ma'am.
Hello?
Yes, ma'am, I'm listening.
Hello?
Please. Anybody can help her?
Ma'am, can you put your question in the chat box? Okay, so you can continue.
All right. So now this is the regression
Sir, for this one, for solving optimization techniques, we are using the matrix process logical expression.
I'm really sorry, but your voice is not at all clear. I'm really sorry, but your voice is not at all clear.
Hello.
Sir, signal I will write on the box, sir. It will not have
madam. Madam,
Okay, madam. You
Right
can
on
keep in
chat
the
box.
chat
your
box.
doubts at the end of the session, please. If any problem is there, you please keep in the chat box. Nagaraj sir?
Yes, sir.
Sir, please mute all.
Okay, right.
Shall I continue?
Yes, sir.
So here the problem is to predict the housing prices. That is the regression problem. So given the problem of supervised learning, what a machine learning recipe does is that it chooses a decision function and the loss function. So decision function here is we have to estimate the outcome as a function of inputs. So the output as a function of input. So the function could be a linear regression or a logistic regression or a neural network. It could be anything. So the output is a function of input. So the function we have to select f, decision function, and the loss function. So loss function is why we have to minimize the difference between the prediction and the actual output and the predicted output. So for that we should have a loss function. So the examples of the loss function include mean square error, cross entropy, and there are hinge loss. There are many other loss functions. So minimizing the loss using the optimization process is all. I mean, once you choose this, you have to minimize the loss using the optimization process, that is gradient descent. So this is the machine learning recipe. Once you have a problem, once you have an input and outputs, you have to select the decision function, loss function, and minimize the loss using the optimization process. So this is a machine learning recipe for this supervised learning problem. So we'll see one of these solutions so that you'll get an understanding of this machine learning recipe. So with our training set defined, how do we use this training set? We pass this training set to the learning algorithm. Learning algorithm gives the hypothesis as the output. Once we get the hypothesis or a model or a function, both are similar, I mean, all are same, hypothesis or a model or a function. Once we get this model, we give a new instance to which we have to make the prediction, and it will give the estimated outcome. Okay, here in this case, size of the house is the input of a new instance. Once you pass this input to the hypothesis, it will give the estimated price. So how do we represent the hypothesis? Is the question now. It's saying we are passing this training set to the learning algorithm. It will give you the hypothesis. But how do we represent that hypothesis? So this representation of the hypothesis varies from the model to model. So in case of linear regression, we represent this as a hyperplane or a line in case of 2 dimensions. If you have 2-dimensional, we call it as a line. If more than 2-dimensional, we call it as a hyperplane. Right. So we are going to represent this hypothesis in case of linear regression as a line. Correct? So, excuse me. So as a line. So what is the equation of line? X plus b, right? So this is of that form, right? Theta naught plus theta 1 x is like line, isn't it? So means here in case of linear regression, we represent y as the linear function of x, and thetas here are the parameters, right? And a linear regression with one variable, we call it as a univariate linear regression, and linear regression with multiple variables, we call it as a multivariate linear regression. So the example that we have seen in the previous slide, we have only one variable, that is size in square feet. So we can call that as a univariate. If you have more than one variable, like size in house, number of floors, number of bedrooms, number of floors, all this information also, if you have multiple variables, if you have, you can call that as a multivariate linear regression. Now the question is, once you're given a data, and if you represent your hypothesis as a line, there are multiple lines that may go through the data. Excuse me. There are multiple lines which may go through this given data, isn't it? So, but then how do you decide which line is the best? Which line is your model? If there is a possibility of having multiple lines for a given data, so which line is the best? How do you determine the best line is the question now, right? So that is where the cost function helps us to figure out how to fit the best straight line to our data. Actually, what makes the line different? If I say theta naught plus theta 1 is the equation of the line, what makes the line different? Two parameters, theta naught and theta 1. So out of this, which is the best line? With multiple theta naught and theta 1, you have multiple lines. Which line is the best? Can I say the line that minimizes the difference between the actual and estimated prices is the best line? Can I say that? So the line that minimizes the difference between the actual and the estimated prices is the best line. So what is our objective now? I have to find a line in such a way that it minimizes the difference between the actual value and the predicted value. Correct. What is the actual value? Actual value is yi. And what is the predicted value? H theta of x. H theta of x is whatever our output or our hypothesis H theta predicts. Right. So H theta of x is the predicted value here and y is the actual value. So our objective here is to minimize the difference between these two values. So can I define a loss function something like this? H theta of x minus yi whole square, sum over I equal to 1 to n. So I want to minimize the difference between the predicted and the actual for all the instances. I equal to 1 to n. 1 by 2m to take average, 2 because to simplify the math in future. We'll see that. So now my objective is to minimize this loss function that I have at hand. Various other loss functions are possible, but there is a theoretical background to take this squared loss for this particular problem, which I don't have in the slides, but it is to avoid mathematics, I did not keep that. Anyway, so there are many loss functions are possible. You can take any loss, but if you take this loss function, the problem will become convex, which is important. So how do we achieve this? How do you find theta naught and theta 1 in such a way that it minimizes this j of theta? So you have to select theta naught and theta 1. You have to learn this theta naught and theta 1, which are the parameters of your model, in such a way that it minimizes the j of theta. So that is where the gradient descent helps us. So gradient descent helps us to learn the parameters in such a way, learn the parameters that minimizes the j of theta. J of theta is your loss function or your objective function that you have defined. Now, okay, everything is well. Now you have defined the objective function and you want to learn some parameters that minimizes this loss function that you have defined. So you have to optimize the parameters. So you have to learn the parameters for that. Right. So we said that is where the gradient descent helps us. But what is gradient descent? What is gradient? And how it helps us to learn the optimal parameters is the question. So gradient, if you see a simple function, a simple line, y equal to mx plus b. If you take the gradient, what is the gradient of this one? Gradient or slope, both are same, right? M. So M gives you slope or a gradient, how steep the line is, right? How steep the line is. Line here is the function, right? And y determines how far we are up, and x determines how far we are along, and b is the value of y when x less than or equal to 0. Okay, if you see the line, can you say whether the line is of positive slope or a negative slope or a neutral slope, zero slope? You can say that, right? If the line is like this in the descent, then we say that it is a negative slope. If the line is ascent, then we say that it is a positive slope. If the line is flat, then we say that it is zero slope. So how do you get the slope of simple line or a function, some function? Okay, so how do you get the slope of this? Slope of this with respect to x as you vary x. Just remember that. Slope of the function as you vary x in this case. How do you get that? If you take a derivative of this function with respect to x, you would get what is the resultant of that? M, isn't it? So you get the slope when you derive with respect to x. X is the varying variable here. So if you want to know the slope of some function with respect to some variable, you take the derivative of that function with respect to the variable that you want to know. Correct? So that gives the gradient. So the gradient is just a vector of partial derivatives. So if you have multiple variables, you take derivative with respect to multiple variables or multiple parameters, and vector of all that resultant will give you the gradient. Understood? Right. If you have any questions, put it in the chat box. We'll answer. So this is the graphical representation of the cost function. So if you suppose if you have a cost function, something like this, right? It is a convex function. So this is where I said the squared loss is important in this for this particular problem. So you have to, as much as possible, you have to select the cost function in such a way that your objective would be convex. It is easy to learn the convex functions. Learn from the convex functions. Right. So this is your objective that you want to learn. with respect to a one variable theta naught, theta 1, sorry. So, I mean, for the simplicity, I just took one variable here, but in our model, we have two variables, theta naught and theta 1. We'll come to that also, but let us understand with respect to one variable, one parameter, theta 1. So as you vary theta 1, as you can see, the cost function is varying like this. It's a convex function. What is your objective? You want to minimize this j of theta. So you want to minimize this j of theta. It means that you want to reach to this valley point. It means that you want to find a theta 1 value in such a way that this j of theta is minimized. So you want to find this theta 1. That is your objective. Correct? So when you randomly initialize theta 1, say for example, initially you have randomly initialized this theta 1. And when you randomly initialize theta 1, your j of theta is somewhere here. If you see the slope of the function here with respect to theta 1, it is negative slope. Correct? In this figure, it is negative slope. So, and what you have to do in order to reach to this minimal point, in this case, you have to increment theta 1 value. Correct? So when the slope is negative here, you have to increment theta 1 value in order to reach to a minimal point. Similarly, if you see this figure, suppose if your theta 1 is here, it means that it is a positive slope. So when the slope is positive, what you have to do? You have to decrement this theta 1 value in order to reach to this valley point, correct? Or the minimal point, right? So can I say, then I generalize this, if the slope is negative, do you have some question? Yes, yes.
Sir, your voice is low, sir.
My voice
Can
is
you
very
hear
low.
me now?
I'm actually shouting.
Very, very low, your voice.
Having that question is that.
Hello, sir.
Yes. Is it audible now?
Now, okay, sir.
Actually, I don't know why. I'm
Of
using the
these,
condenser
you have
micro.
seen.
I'm getting
Srinivas,
noise.
sir.
Please mute that.
Srinivas, sir.
Oh,
Right. Is it audible now?
Yes,
yes,
sir.
sir. Yes, sir.
You're audible, sir.
Okay. But I don't know why. I'm actually, my voice is loud and I'm using condenser microphone.
Yes,
I
yes.
don't. So anyhow, so now we can conclude from this that if the slope is negative, we have to increment theta 1 to reach to the minimal value of j of theta, and if slope is positive, we have to decrement theta 1 to reach to the minimal value of j of theta. So this is applicable for if you have multiple values also. So you can visualize if you have multiple parameters like this, like a bowl. If you have two parameters in a multi-dimensional, it is much more complex graph than this, right? So if you have two dimensions, you can imagine it as a bowl and you want to reach to the bottom of that bowl. So you have to modify two parameters here, theta naught and theta 1, in such a way that it reaches to this valley point, right? So what I'm trying to say here is that if the slope is negative, you have to increment it. If the slope is positive, you have to decrement it. Correct. So is it okay if I do this? Theta j equal to theta j minus alpha times derivative of j with respect to theta j. So this derivative of j with respect to theta j will give me the slope. So if this is negative, negative times negative.
Sir,
Voice
sir,
is totally mute.
sir, you.
I don't know. I did not do anything. Somebody muted me.
Okay, okay.
Okay. Anyhow. So it was not audible to you, right? From the beginning of this slide or from the previous slide?
Yes, sir.
No, sir. Is it audible, sir?
Okay. So what I want to do is, who is doing all this?
Sir, please off the annotation, sir.
Me? I didn't do anything actually. You're telling to me or somebody else?
Please continue, sir. This is good.
Okay. So repeat this. So is this okay if I do the following procedure? Like
Previous slide, sir. Previous slide. From previous slide.
This is totally unmuted. I mean, it's not. Was it not covered totally, or part of it is not covered?
Sir, for this work, for showing the simulation of these type of functions, which software can MATLAB can be.
I did not get our question. If somebody can explain to me, I'll answer that. Voice is breaking. Can somebody respond?
Sir, you please continue. I will take care of that.
Okay.
Sir, we are audible.
Sorry for the disturbance. You can please continue, sir.
So here what I'm trying to say is that you have to learn your parameters, theta naught or theta 1, whatever, in such a way that your j of theta is minimized. So you want to reach to this volley point. So you want to learn this theta 1 where j of theta is minimum, right? So when you randomly initialize, the parameters that you have initialized randomly may not be optimal parameters, but you have to progress towards the optimal parameters, right? So for example, when you randomly initialize, your theta 1 is here. It means that your function is somewhere here. J of theta is some value here. If you observe here, the slope of this is negative, right? One request to the organizers, somebody annotating the screen, okay, which is actually creating a disturbance to me. Right? Please stop that.
Okay, sir. Okay.
So if the theta, so if the slope of the function is negative, as you can see in the figure,
Sir, please go ahead with your screen sharing, sir. I have
I
disabled the
don't know what is
annotations.
happening.
Yes, I have disabled the annotations. Please go ahead, sir. Why? Because someone is else annotating on the screen, right? So I have disabled all the screen. Please go ahead.
Give me a second. So if the slope is negative, in order to reach to the minimal point, I have to increment the corresponding parameter. If the slope is positive, I have to decrement the corresponding parameter. So is this okay if I do this? Like for example, if I say theta j equal to theta j minus derivative of j with respect to theta j. As I have already mentioned, this derivative of a function with respect to a particular parameters will give the slope of that function with respect to that parameter or that variable. Right? So this derivative will give me the slope. What happens if this derivative or the slope is negative? If the slope is negative, negative times negative, it is positive. It means that I am incrementing this theta j. Similarly, if this derivative or the slope is positive, it means that I am decrementing theta j. Right? So what I'm essentially doing here is that if slope is negative, I'm incrementing theta j. If the slope is positive, I'm decrementing theta j. Right? So, and alpha here determines the step size. Okay, how much, I mean, what is the step size that I should take? How much I should decrement or how much I should increment? Correct. One question, this annotation that I'm seeing on the screen, is that visible to me only or to you also?
Graph is visible, sir.
Not the graph. I'm getting some random arrows, random
No.
lines.
No.
That is not visible to you?
Yeah, not visible. Only your screen is shared.
Okay, but why I was disturbing is that I was getting lot of arrows.
No, someone was doing annotation. I think the organizer has blocked them.
Now also, even now, after you said that also, it is visible to me.
Yes,
Anyhow.
sir. Even we are getting the annotations. Just now I have seen the horizontal red line coming, and here and there all the arrow marks are coming. It is actually irritating. I don't know. Please kindly the organizer should take care of all this.
Hello. Sir. Please, all the attendees are requested to do not do any such kind of things in live session. Please, because
Sir, host can disable annotation, sir. Please do it, sir.
Yeah, that sir has to do. Venkateshwara sir.
Yes, sir.
Venkateshwara sir.
Yes, sir. Once again, I have disabled the annotation, sir. Please go ahead, sir, Venkateshwar sir. If someone will annotate, the names will be displayed on the screen, sir. Please be careful on while annotating. Thank you, sir.
Okay.
Please go ahead, sir, while sharing.
We are all teachers, sir. I think we should have some ethics. Please, who are doing it, please think about yourself. You are a teacher.
Sir. Sorry for disturbance. Please go ahead, sir, Venkateshwar.
Okay. So I initialize theta naught and theta 1, which are the parameters that I'm supposed to learn. And I repeat the procedure. I update this theta, theta j, that is all the parameters using this procedure. So this algorithm, we call it as a gradient descent algorithm. So that is when the gradient is negative, we are incrementing theta j. And when the gradient is positive, we are decrementing theta j. And the derivative of this j with respect to theta naught is this, and derivative of j with respect to theta 1 is this, as you can see in the slide. So that is univariate linear regression. What about if you have multiple input variables? Like in addition to the size in square feet, suppose if you have a number of bedrooms, number of floors, age of the home, multiple variables, multiple input variables. So your input is now a feature vector, not a single value. Right? If you have multiple variables, then we call it as a multivariate linear regression. And previously our hypothesis is just theta naught plus theta 1x. Now with the multiple variables, our hypothesis would be theta naught plus theta 1x1 plus theta 2x2 plus theta 3x3, so on, theta m xn. Theta n xn, where m is the number of features. Here we have 4 features, so that is why we have 5 parameters, theta naught plus theta naught to theta 4. Right. So if I take x naught as a 1 to generalize this, so I can say it is theta naught x naught plus theta 1 x1, theta 2 x2, so on, theta 4 x4, isn't it? So your hypothesis is now you can, in a vectorized form, you can represent it as a theta transpose x. So here also the cost function would be the same. Only thing is that our h theta of x is changing now. Earlier it was theta naught plus theta 1 x1, theta 1 x. Now here it is theta naught x plus theta 1 x1, theta 2 x2, so on theta 4 x4. Only thing is that hypothesis is changing, but not anything else. Gradient descent is also same. Here you will get a different, instead of theta naught and theta 1, you will get 5 different parameters, theta naught to theta 4. So you'll have to simultaneously update them. Simultaneously means that, so when you are updating, say for example, theta of 3, okay, there may be theta naught and theta 1 also in that, other parameters also in that. So those parameters you have to take it from the previous iteration, but not the updated parameters that you have updated in this iteration. So that's what I mean by simultaneously update. And regularization, we'll see why regularization is important with the help of some example. Let us take a data. Okay, so I've generated this data using sine 2 pi x. So this is the underlying function. The green one is the underlying function from which we have generated this data, right? Then added some noise to it and generated 10 points randomly. And this is the data, this is the input data to which we would like to learn the hypothesis. So if I just say my function is theta naught, that means m equal to 0, correct? It is zero order polynomial, just theta naught, nothing else. So I'll learn the horizontal line, right? So which is not a better fit to the, as you can see, it is not a better fit to the actual data. So you have to learn the data which is something close to this green line. I mean, you have to learn the hypothesis which is something close to the green line in order to actually exactly represent the input data. But then this deadline is nowhere close to this green line. So it is not a better best fit to the data, right? So say you take first order polynomial, that is the linear regression, theta naught plus theta 1 x. So the line would be like this, somewhat better than the previous line, but this is also not actually greatly representing the input data. Suppose if you take third order polynomial, that is theta naught plus theta 1 x plus theta 2 x square plus theta 3 x cube. This is your model. Then it is, very much close to the green line, but then at exact representation. This is actually better model than all the previous models. If you take ninth order polynomial, say for example, that is theta naught plus theta 1 x plus theta 2 x square, so on, theta 9 x power 9. If you say this, you see the red line is going through each and every input data, each and every training point, which means that it is the training error is 0 because it is going through each and every data point. The training error is 0. But do you think it is the actual representation of the input data? No, right? So given any new instance, it will not be able to predict it well because it is not actually representing the model, underlying model, correct? So what's going wrong here is that in a process of fitting to each and every training point, what you are doing is that you're oscillating this model too much in between these data points. It means that there is a lot of variance in your data, in your model, correct? So you're trying to overfit to the training data. So how do you avoid this overfitting? If I observe these parameters underneath this model, if you see this W0 to W9 are equivalent to your theta values in this model, theta naught to theta 9. So if you see this 0th order polynomial, the range of, I want you to observe the range of these parameters. At m equal to 0, the range is small. M equal to 1, range is small. M equal to 3, reasonably small. But if you see m equal to 9, the range of values, the range of these parameters is too high. Correct. So in a process of fitting exactly to the training data, you have no restriction over the parameters that you have in our model. So that is why it is going anywhere in any range, and oscillation is happening here. It means a lot of variance is happening in the model, which is leading to the overfitting of the data. So overfitting is a situation where you fit exactly to the training data, but it will not perform very well on the testing data. Correct. So that situation we call it as overfitting. So overfitting is happening here, correct? As you increase the complexity of the model, correct? So how do you avoid this overfitting? One thing that I could do here is that one possibility is that increasing the data set size, but which may not be in your hand all the time. Another thing that you could do is that you have some restriction over the parameters, right? So it means that you penalize high weights that contribute to high variance and sensitivity to outliers. How do you do that? How do you penalize the weights? If you add this theta values to the cost function, anyway you are minimizing this cost function or the loss function, so you will also try to minimize the other part, that is theta values. So that is how you penalize the high weights that contribute to high variance. So lambda here is like your alpha in the gradient descent algorithm. It determines the weight that you give to this part of the loss function. I hope you understood, right? So that is about the linear regression and the regularization. The purpose for providing the linear regression and regularization is to understand the concepts like gradient descent and regularization. Correct. So now the logistic regression for the classification, which is a different model. This is for the classification. This is also forms the basis for your neural network. Okay, I'll quickly try to finish. Okay, so here it is a probabilistic model to learn a classifier. It says that here h theta of x is z of theta transpose x. If you see in the previous model, in case of linear regression, your hypothesis is theta transpose x, but here it is z of theta transpose x, right? So it means that you are trying to say if theta transpose x is some value, it is one side of the line. If theta transpose x is another value, it is the other side of the line, right? So if the theta transpose x is a large positive value, then it is a positive instance. If theta transpose x is a negative value, then it is negative side of the x. So how do you say that? So you can define a z as 1 by 1 plus e power minus z. What happens if z is large positive value? Then this quantity e power minus z is almost 0. Correct. So if almost 0, it means that it classifying it as 1. Right. What happens if this is a large negative value? Then this is very high value. The denominator is very high value, close to infinity. 1 by infinity it is 0. Then you are classifying it as a negative instance. Right. So that is what you are doing in case of logistic regression. So if you observe, the only thing that is changing here is that the cost function h theta of x. With this cost function, what would be the what would be the loss function? Now the cost function is changed. What would be the now the cost hypothesis is changed. What would be the cost function? So can we use square loss, which we have described earlier? We cannot use, because using the cost function as a squared loss will result in a non-convex optimization for this particular hypothesis, right? So this will result in a non-convex hypothesis, non-convex optimization, if you use squared loss with this hypothesis, with this new hypothesis. So for this reason, we use a different loss function. Logistic regression objective now is sum over I equal to 1 to m yi log h theta of xi plus 1 minus yi log 1 minus h theta of xi. So this is the new cost function that we have at hand. So in any loss function, just remember that our objective is to minimize the differences between the actual and the predicted. It means that the loss function is trying to see that if you predict it correctly, loss is 0. If you predict it wrongly, penalize the loss function or the cost function with some positive value. So this is what you have to do in any of the loss functions. Let us see whether this loss function that we have defined for the logistic regression is doing that or not. So I'm just repeating. If the prediction is correct, the loss should be 0. If the prediction is wrong, then loss should be penalized with some positive number. So if I unroll this cost function, this one, if yi is 0, then this part would be 0, right? It means that you're only considering this part. If yi equal to 1, it means that I'm not considering this part. This part will become 0. I just consider this part. I'm sorry, the negative value is missing here. Minus should be there. That is missing there. So if I unroll that, I'm just taking minus log h theta of x if y equal to 1. I'm taking minus log 1 minus h theta of x if y equal to 0. This is what I'm taking, right? From the previous cost function only. I just unrolled it. If I take two classes 0 and 1, binary classification problem, 0 or 1. So I'm just taking this. So what it is trying to do, when the prediction is wrong, if y equal to 1 and h theta of x equal to 0, then it is the wrong prediction. Similarly, if y equal to 0 and h theta of x is equal to 1, that is also wrong prediction, right? And y equal to 1, h theta of x is the correct prediction, x equal to 1 is the correct prediction, and y equal to 0, h theta of x equal to 0 is also a correct prediction. So for the correct prediction, the cost should be 0. For the wrong prediction, it should be some negative value, sorry, positive value, right? Let's take a scenario of wrong prediction. If y equal to 1 and h theta of x equal to 0, right? So if h theta of x equal to 0, then what is the cost? Minus log of 0. Okay, what is 0? What is minus log 0 here? Which is some negative value, right? Some negative value. For 0.01, it is around 1 minus 1.5. For 0, it is much higher value. Correct? So because it is giving some negative number, negative of negative is positive, right? It means that when the prediction is wrong, you're adding some positive number to the cost, so which is satisfying our criteria in defining the cost function. Let us see when the prediction is correct, that y equal to 1 and h theta of x is also equal to 1. So what is minus log 1? Minus log 1 is 0. So it means, sorry, log 1 is 0. So minus 0, 0. So it means that you're not adding any cost to the loss function, right? So the criterion is satisfied. If the prediction is wrong, you penalize it. If the prediction is correct, do not penalize. So this is satisfied. There is some probabilistic background for this. We'll avoid that method. Now with this, to avoid overfitting, for this cost function also you can add the regularization term here. And gradient descent also the same thing. You can learn the parameters using the gradient descent algorithm, that is initialize theta, repeat until convergence, theta j equal to theta j minus alpha times derivative of j with respect to theta j, right? And these are the derivatives of j with respect to theta j. Now, okay, so we have finished the machine learning basics. In this, we have learned what is gradient descent, what is regularization, what is logistic regression, correct? So we'll see now with all these basics that we have formed in the previous slides, we'll see what is neuron, what is neural network. Okay, so ANN with a single neuron cell is equivalent to logistic regression. So when you say neuron or a perceptron, which is equivalent to logistic regression, that's whatever that we have just described just now, right? So ANN with a single neuron cell is equivalent to logistic regression. First, let us try to understand the logistic regression with a neural network mindset. Then we would explore the ANN with multi-layers and neurons. So if you see this artificial neuron, which is taking inputs, multiplying these inputs with the weights, and taking net sum of that resultant, and passing this net sum to a sigmoid function. The sigmoid function is 1 by 1 plus e power minus net. This is what it is doing, right? If you observe the logistic regression, the same thing we are doing. Theta transpose x or w transpose x is just sum over I equal to 0 to n wi xi. Means that you are taking net sum and you are passing it to z of z, right? So z here is net sum and z here is a sigmoid function. Correct. The same thing you are doing in case of neuron also. So that is why we call the single neuron as a logistic regression, is equivalent to logistic regression. This neural network, a group of these neuron units together forms a neural network. So the below is the representation of such network. Here x0 and a02 are the bias terms that we add. Like for example, theta naught we are adding, no? So this is the term corresponding to that input corresponding to that theta naught, x0, which is equivalent to 1. Similarly here, a02, which is equivalent to 1. Okay, so we give the output of this neurons at layer 1 as an input to the neurons at layer 2, and output of neurons at layer 2 as an input to the neurons at layer 3, and so forth, right? And at layer 1, inputs are the actual input, neurons are the actual inputs, x1, x2, x3 are the actual inputs. And here in this case, in this example, layer 3 it is the output layer, and layer 2 is a hidden layer, layer 1 is the input layer. So you can have more than one layer. If you have more than one layer, we call that as a deep neural network. If you have just one layer, we call that as a shallow neural network. So why do we need neural networks? Now the question is, why do we need neural network? Why do we need neural network is the question. Why not linear regression or logistic regression? Why we have to go for the neural network at all? So let's have a look at linear regression and logistic regression and disadvantages of them, and how they learn the complex nonlinear hypothesis. So if you take a linear regression, if you want to learn this hypothesis with a zero order polynomial, I mean with the first order polynomial, this would be theta naught plus theta 1x. If you see the second order polynomial, the hypothesis would be theta naught plus theta 1x plus theta 2x squared, like this, which is actually learning the nonlinear hypothesis. Third order polynomial, then theta naught plus theta 1x plus theta 2x squared plus theta 3x cubed, which may learn more complex hypothesis, which may better than this model, right? So with this is with the one example, I mean one input variable. Just remember, input variable here is x. So with one input variable for the third order polynomial, you will have to learn 4 parameters. Let's take 2 features, x1 and x2. So linear regression first order polynomial is theta naught plus theta 1 x1 plus theta 2 x2. For the second order polynomial, it is theta naught plus theta 1 x1 plus theta 2 x2 plus theta 3 x1 square plus theta 4 x2 square plus theta 5 x1 x2. It means that you are including all the second order terms also. All these last 3 terms are the second order terms, right? Similarly, if you go for third order polynomial, you include all third order terms also. x1 cube, x2 cube, x1 square, x2, x1, x2 square, all these new terms you have to include in the third order polynomial, right? So with 2 input variables, third order polynomial will have to learn 10 parameters. Okay, and similar in the case of logistic regression also. Only thing is you just pass this net sum to sigmoid function. That is the only thing, sir. But the parameters would be same, right? What if we have 100 features? How many features that you will have to learn? How many parameters that you will have to learn for second order polynomial if you have 100 features? With 2 features, second order polynomial will have to learn 6 parameters. It means that you will be scaling this to 6 features, and you will have to learn 6 parameters. 5 features, 6 parameters. Sorry. What if you have 100 features? You will have to learn around 17,000 features. Means that you will have to learn 17,000 parameters with 100 features and second order polynomial. If you go for a higher order polynomial, which is much more than these number of parameters, do you think it is possible? It's not, right? Which is very hectic, learning those many number of parameters. Right. So how this hectic thing is avoided using the neural networks? How it reduces? Yes.
So sorry, sir, for the interrupt. Now it's time for break, 5 minutes, sir.
Okay, no problem.
Yes. Dear participants, we'll be back within 5 minutes. Thank you. Venkatesh sir?
Yes, ma'am.
Yeah, you can start the session.
Somebody raised the hand. So let's take a non-linear hypothesis and see how neural networks learn this. Am I audible?
Yes, sir.
Yes.
Okay. So we'll take one nonlinear hypothesis and see how the neural network learns this. So nonlinear hypothesis I took here is XOR at X0. If you see XOR at X0, if you take both the inputs as 0 XOR, then it is 0. Both the inputs are same, then it is 0. If they are different, then it is 1. Similarly, if you take XNOR, it is reverse. If the both inputs are same, then the output is 1. If both the inputs are different, then the output is 0, isn't it? So this is how we can represent this in a two-dimensional plane. If you take more instances of this, it is somehow looking like this, right? So this is not linearly separable data, isn't it? You cannot draw just a line to separate these two classes. So this is a nonlinear hypothesis. So how you learn a hypothesis to represent this nonlinear data. Simple example, if I see, that is this must be AND gate, isn't it? I couldn't see my screen. Simple example of AND gate. Yeah, AND gate. The simple example of AND gate, right? So if you take the weights as this minus 30, 20, and 20. Your inputs are this x1 and x2 are this. It can be 0, 0 or 0, 1 or 1, 0 or 1, 1. Anything. X0 is a bias value, 1, which is equivalent to 1. Right. So if you take these as the weights, minus 30 and 20, 20. So you can represent this and using this neuron, right? Artificial neuron. Say what happens, let's say, if my input is 0 and 0. If input is 0, 0, then this net sum would be minus 30. What is z of minus 30? Z of minus 30, 1 by 1 plus e power minus 30. Minus of minus 30, which is a very high number in the denominator, very big number in the denominator. So therefore, the whole thing would be equivalent to, nearly equivalent to 0. 1 by infinity is 0, isn't it? So this is 0. Similarly, if I take 0, 1, then in that case, I would get minus 10 as the net sum. In that case also, output would be closely equivalent to 0, right? Almost equivalent to 0. And similarly, if I take 1, 0, in that case also it is minus 10. Z of minus 10 is close to 0. If I take 1, 1, then I get positive number here in the net sum, that is minus 30 plus 20 plus 20, that is 10. So Z of 10 is equivalent to 1. 1 by 1 plus e power minus 10. So e power minus 10 is almost equivalent to 0. 1 by 1 plus 0 is equivalent to 1. Right. So I can learn this AND gate using this neuron with the weights as minus 30, 20, and 20. So this is one logistic regression, correct? So using the logistic regression, I can learn the AND gate with one neuron, that is with the logistic regression. Similarly, I can also learn OR gate, right, with the weights as minus 10, 20, 20. If I take minus 10, 20, 20 as the weights, so the hypothesis would be z of minus 10 plus 20 x1 plus 20 x2. So for 0, 0, it is giving output as 0, 0, 1, 1, 1, 0, 1, 1, 1, 1. Right. So I'm not going in it because we have already explained one example. So you can see, you can substitute 0, 0, 0, 1, 1, 0, 1, 1 in this, and you can see that you will get this outcome 0, 1, 1. I can also learn NOT gate, NOT x1 and NOT x2 gate, right? So I can also learn that with a different weight, right? So for NOT gate, it is the weight 10 minus 20. Similarly, for the other gate, it is 10 minus 20 minus 20. Correct. So you can all learn all these individual gates using this logistic regression or a single neuron or a perceptron. Right. Can I combine multiple of these gates to get an XOR gate which is non-linear? Okay, so putting it all together. The AND gate, I take this as the AND gate. You can see the corresponding weights that are coming to this. Minus 30, 20, 20. Right. So this outcome of this A12 is the AND gate. That is 0, 0, 0, 1. If I take 0, 0, 0, 1, 1, 0, 1, 1 as the input. Correct. So for this input, this is the output. For this input, this is the output, and so forth. At this neuron, at this activation unit. Correct? And similarly, I take not x1 and not x2 gate here. So I get this output, 1000, like, which we have seen. Right? So you can observe the corresponding weights. 10 minus 20 minus 20 that we have learned. Correct. So now I give these two as the input to the OR gate. These two as the input to the OR gate. What I would get? 0, 1, 1 I would get. 1, 0, 1 I would get. For both the zeros, I get 0. Okay. If you see, this is the output of XOR, isn't it? So with something that you couldn't achieve with single neuron cell, you can combine multiple of them and achieve that, because it is inducing nonlinearity into the model, right? So that is why you have to go for the neural network. And you can see there are very few parameters that you have to learn here. So these are some notations that we are going to use. So X0 and A02 are the bias terms, the top wala. And layer 1 and layer 2 have 3 units each. X1, X2, X3 in layer 1, A12, A22, A32 in layer 2. And layer 3 is the output layer. Layer 1 is the input layer. Okay. So activation unit, A is referring to the activation unit. If the superscript is 2, it means that it is in the layer 2. If subscript is 1, it means that it is unit 1 in a corresponding layer. Subscript 2 means second unit in layer 2. Subscript 3 means third unit in layer 2. Layer 2. If it is in the layer 3, then you can represent this as a A13. It is in layer 3 and unit 1. Right. And to represent these weights, which are in between layer 2 and layer 1, you use theta 1. Okay. So if it is between the layer j and layer j plus 1, you use theta j. Right. So if you have if you have 3 input units, 3 units in layer 2 and 3 units in layer 1, how many parameters do you have to learn? 3 by 4, right? 3 by 4. 4 you are including bias term also. Right. Total 12 parameters you'll have to learn. Correct. From 4 units to 3 units. Total 12 parameters you'll have. 3 by 4. Right. So you compute this activation units, the outcome of each of these activation units in a forward propagation manner. Say for example here, A12. In order to compute this, you take all the inputs that are coming to this, X0, X1, X2, X3. Correct. Multiply them with the corresponding weights. Theta 101 X0, theta 11 X1, theta 12 X2, so on, which is equivalent to theta 0 X0, theta 1 X1, theta 2 X2, theta 3 X3, something like that. But different weight, because you have a different weights, you have a different notation here. You have multiple weights, that is why you have a different weights. So these are the weights corresponding to the edges that are coming into this particular activation units. So with that weights, you multiply these input variables and pass it to the sigmoid function z. Then you would get this activation unit. Similarly, you repeat the same for other activation units at layer 2. A22, you get inputs are multiplied with the corresponding weights, pass it to the sigmoid function. Similarly for activation unit 3. Once you get all these activation units at layer 2, you pass this as an input to the layer 3. That means that you take these as an input. In place of x0, you put these activation units and multiply them with the corresponding weights and pass it to the sigmoid function. So you would get h theta of x, which is the actual prediction. Right. So because h theta of x is the actual prediction, and you know that, sorry, h theta of x is the prediction, and you know the original value also. What is our goal? Our goal is to minimize the difference between this actual and the predicted. Correct. So for that we have the objective function at hand, which is the same thing. I'm skipping this. So for example, if you have a multiple classes, I'm skipping few things because I am doubtful whether all of you are getting the mathematics or not. That is why I'm skipping the mathematics part, trying to explain in simple terms. So that is for this binary classification problem, right? The whatever that we have seen in the previous slide is for the binary classification problem, 0 or 1. What would you do if you have a multiple classes, right? So you can represent it with this vector. So for example, if you have 4 classes, pedestrian, car, motorcycle, and truck, and you want to classify any instance into one of these classes, one of these 4 classes. So in that case, you can represent your hypothesis as a vector. So wherein 1000 corresponding to pedestrian, 0100 corresponding to car, and 0010 corresponding to motorcycle, 0001 corresponding to truck. Right. So if this output is 1, it means it is a pedestrian. If this output is 1, then it is a car. If this output is motorcycle, sorry, 1, then it is a motorcycle. If the last output is 1, then it is a truck. That is how you represent. And so this is how you do prediction at unit 1, prediction at unit 2, prediction at unit 3, prediction at unit 4. Okay. So if the actual is pedestrian and you also predict as a pedestrian, then you expect the outcome as 1000. Your input is also, your original ground truth is also 1000. Right. So the cost function for logistic regression, that is when you have a one single output unit, it is something like this, right? For logistic regression, minus 1 by m sum over equal to 1 to m by log a. This we have already seen, right? So this is with a single neuron, right? With the, if you have a single neuron at the output layer. What if you have a multiple units at the output layer? You have to take the cost at each and every output unit and take sum over that, isn't it? So for k equal to 1 to k, where k is the number of classes. So you have to take the cost at each and every output unit and take the sum over that. So this is the only additional thing that we are adding here. And also here, earlier you are just taking j equal to 1 to n theta j square. It means all the parameters in this model. Here also you have to take regularization for all the parameters in the model, but here you have more number of parameters over the many layers, right? So you have to take regularization with respect to multiple parameters. So now the question is, everything is fine. Now we have a model. How to learn the model, how to predict, we know. And we also know the objective function that we want to minimize. And we have some parameters to learn to minimize that. So parameters here are theta lj ij, isn't it? For over all the layer cell. Correct. So you have multiple parameters in that. Now the question is, how do you learn these parameters? How do you learn the parameters over the network? Okay. Simple way is compute gradient with respect to each and every weight that is there in the network, each and every parameter that is there in the network. Apply gradient descent to update the weights. That is theta ijl equal to theta ijl minus alpha times derivative of j with respect to theta ijl. Right? It is very easy. So this is a brute force approach, but then it is time intensive and redundant calculations you have to do. Redundant calculations in the sense, maybe part of this is already, when you are updating a particular parameter, part of the computation required for that updation of parameter is already there, already computed, but you are again doing it. Okay. So that is redundant calculation. And if you go for the brute force approach, to avoid that, we have a backpropagation algorithm. It is a kind of dynamic programming wherein you store these parts that are required for the further computations in some table and use them without recomputing them again. So it's a kind of dynamic program. So it avoids redundant computations. So this is forward propagation. You assign the input layer as activation units at layer 1 and you compute net sum theta transpose x kind of theta 1 a1. You get the net sum here. To pass it to the sigmoid function, you get the activation units at layer 2 and so on. You repeat the procedure till the last layer. At the end, you will get the output layer, which is your prediction. So A capital L is h theta of x, which is the prediction. So with the hypothesis defined now, h theta of x. So can I get the error at the last layer? I can get the error at the last layer, right? So once I get the error at the last layer, I can propagate the error back to this previous layers to understand how much of this error is from a particular unit. Say for example, 5 of you or 6 of you have organized this workshop or FDP. Okay, A, B, C, D, E, F are the names of the organizers, say for example. Okay, so for example, A has contributed 30% to organize this FDP. B has contributed some 20%. If something goes wrong, A should take the blame of 30%, isn't it? Suppose A has some subordinates, some XYZ under him. Each of them has contributed 5%, 5%, 5%. Again, this 30% of the blame will be shared by these subordinates XYZ by 5%, 5%, 5%. What you're doing, if something goes wrong at the output layer, you're propagating this error back to the previous layers. Correct? So here also, if something goes wrong, or it means that if something wrong at the output layer, you have to propagate the error backward to the previous layer, starting from the output layer. So if this is the error at the last layer, derivative of L with respect to AL minus Y. AL is the predicted one and Y is the actual one. Okay. So now the error term for the previous layers are calculated as this. This is the error at the last layer, that is the output layer. Previous layer error is multiplied with the corresponding weights times derivative of cost function with respect to net sum at that particular layer, a particular unit. Okay, and this is how you compute this G of Z. So once you have this error, you can compute derivative of J with respect to theta ij using this error at that by multiplying with aj n. See, if you observe, you can directly get this instead of computing all that. Right? I just wanted to observe that. If you compute all this, you'll have to again compute this delta Lij, all that, right? I will see the example anyway. I'm just taking off the mathematics. Okay, I'm trying to demonstrate using the example. Somebody again writing on the screen. So these are all affects the session actually. I don't know, but who was doing this? Anyhow, so let me finish quickly. So Z1 of 2, which is the net sum. You have input variables x1 and x2. I avoided bias term for the simplicity. So you have x1 and x2. How do you compute a12? You have to compute the net sum first. That means you multiply with the corresponding weights x1 theta 111 plus x2 theta 121, all that. And similarly, a12 equal to sigmoid of z12. Give this net sum as a and to the sigmoid function. It will give you the activation unit a12. This one. Similarly, you do this a22. You compute the net sum here and give it to the sigmoid. You get a22. Now take this as input to the next layer and compute a13. That is net sum here by taking theta 12 a12 plus theta 122 a22, and h theta of x is a13. That is z of z13. Correct. So h theta of x is this, right? So output you have got now. This is forward propagation for this example. Now let us see the backward propagation. So let us try to understand this. If you do brute force approach, what will happen? If you do this backward propagation, what will happen? How is it saving some time? How is it avoiding redundant computation? That is what I am trying to demonstrate. Correct. So if I take derivative of j with respect to theta ij, okay, if I use the formula that is mentioned in the previous slides, I can get it by using this formula, that is ajl delta I l plus 1. Correct. So which I substitute, if I substitute here, that is derivative of j with respect to theta 112, theta 112, right? If I substitute that, which is equivalent to a12 times delta 13, delta 13 at the output layer, that is h theta of x minus y, right? So I can directly get this, right? If I substitute this in the formula, right? So if I do it manually, derivative of j with respect to theta 112, using the chain rule, I can write it as this: derivative of j with respect to h theta of x and times derivative of h theta of x with respect to z13 and derivative of z13 with respect to theta 1. This is the chain rule. Let us try to compute one by one. See, if I compute this derivative of j with respect to h theta of x, okay, what is j? J is this, correct? If I take derivative of j with respect to h theta of x, then it would be yi times log of x with respect to, I mean, derivative of log of x with respect to x is what? 1 by x, right? So derivative of h theta of x with respect to h theta of x is 1 by h theta of x. So I get 1 by h theta of xi. Similarly, for this part, 1 minus yi, 1 by 1 minus h theta of xi, derivative of this again is minus 1. So I would get this yi minus h theta of xi by h theta of xi, 1 minus h theta, if I solve this. Okay. Now this part is done. Derivative of j with respect to h theta of x. Let's take another part. Let's take this derivative of z1 with respect to theta 112. So z13 is this. If I take derivative of with respect to theta 112, I would get a12. Another part that is left here is derivative of h theta of x with respect to z13. Okay. So what is h theta of x here? 1 by 1 plus e power minus z. So derivative of h, sorry. So g of z, right? H theta of x is g of z. That is 1 by 1 plus e power minus z13. So that with respect to z13, if I take this, as you can see in this, if I take derivative of x, sigmoid of x with respect to x, if I solve this, I would get this derivative sigmoid f x times 1 minus sigmoid of x. This is derivative of sigmoid of x with respect to x. I would get this sigmoid of x times 1 minus sigmoid of x. So if I substitute this in this formula, derivative of z of, which means sigmoid of z13 with respect to z13, I would get this z13 is equivalent to h theta of x. Sorry, z of z13 is equivalent to h theta of x. So which is equivalent to h theta of x times 1 minus h theta of x. So that is equivalent to sigmoid of z13 times sigmoid of 1 minus sigmoid of z13. Correct. So if I combine all of them together, I would get what? Delta L times AL J. That is this A12 times delta 13. I got that right? So I need not do all that. I just have to substitute in that. Directly I am getting. So which is avoiding lot of computation. Correct. You see for another level. So now I took derivative with respect to this parameter, which is just previous to this. So let's take parameter in the previous layer, theta 111. If I take that using the chain rule, I can write it as this: derivative of j with respect to a13, derivative of a13 with respect to z13, z13 with respect to a12, a12 with respect to z12, and z12 with respect to theta 1. So if you observe this, these two terms, derivative of respect to a13, that is h theta of x, and derivative of h theta of x with respect to z13. a13 is equivalent to h1 h theta of x. Just remember that. These things are already computed at the previous layer, correct? And we have the result. Why you have to compute it again? You need not compute it again, right? Because you have already computed them. Similarly, if you solve this, you would get this a11, a12, 1 minus a12, These are all the things we have computed either in a forward propagation or as part of backward propagation. So you just have to substitute them. So backward propagation, if you use, it will ensure that you need not recompute them again. So you just have to substitute them. So that is why it saves lot of redundant computations and therefore lot of time. So that is why back propagation we are saying it is a kind of dynamic program. Correct? So so applications of neural networks including classification of data, anomaly detection, speech recognition, audio generation, machine translation, and many other, almost in every domain this neural networks has applications. Yeah, thank you very much. If you have any doubts, I'll take. My tone in between has affected due to this disturbance. So if you feel uncomfortable with my tone, I'm sorry for that. Yeah, thank you. I'm done. Any doubts I can take.
Thank you, sir. The participants, if you have any queries, please. I think no queries.
Okay, thank you very much.
Yes. Thank you so much, Venkateshwar sir, for your wonderful session. And sorry for a little bit disturbance. And thank you for accepting our invitation in spite of your busy schedule. Thank you, sir. Thank you so much.
All right, thanks.
Yes. Srinivas sir.
Hello.
Sir.
Yeah, I'm here.
Yes,
Just
sir.
1 or 2 minutes. 1 or 2 minutes. We'll see. We'll see.
Hello.
Yeah, Aditya sir.
Yes, can I speak to Venkateshwar sir? Is he available?
Yes, sir. 1 second. Abhinav, sir is there?
Let me check. Wait.
Yeah.
Hello.
No, ma'am.
Okay.
I
Not
think,
an issue.
has left.
Not an issue, ma'am. Like,
Okay.
only request is if you can share an email ID, that would be fine. That would be more
Yeah,
than
we'll share, sir. We'll
Well,
share.
because like only thing is, since past 4 days the event was going so very well. It was like absolutely you are maintaining an international standards. I would say, like, there is no doubt in that. But only today we had lot many disturbances. Even I could not join on time. After 15 minutes I logged into. Somehow I got. Thanks to you, Jayashree ma'am. You gave me
Yes,
the
yes,
ID
sir.
and password. I could somehow manage to come in. But today's session was, the topic was very, very complex. I know, neural networks, and at the same time,
Yes, sir. Yes, sir.
there was some disturbance, but still not a problem. Because you have one more flexibility of looking it into YouTube. We can browse it again and go through
Yeah.
the concepts again. So
Yes,
once I
sir.
go through the concept of neural networks again in depth, then I can have some doubts. Already I
You
have
can
so
personally
many.
contact him also, sir.
Yes,
It's
sir.
not
Yes,
an
ma'am.
issue.
Only thing is,
Yeah.
if sir is available, if he can share an email ID, that would be great.
Yeah, we will share of all the resource persons, sir,
Yes,
in
sir.
Telegram group. Yeah.
Okay. And apart
Yeah.
from that, everything is fine, ma'am. And coming to
Thank
last
you.
4 days, it was really fantastic.
Thank you.
That's only single line feedback.
Thank you, sir. Thank you so much.
Thank you, ma'am. Thank you.
Dear participants, now we have a valedictory session. Please stay tuned.
Very good organizing, madam. All were really good. All resource persons were really nice.
Thank you so much, Krishna sir.
Very knowledgeable. Really very knowledgeable. Actually,
Thank you, sir.
I'm from
Okay,
Bangalore.
sir.
No, even AICT FDPs won't be like this with so much of good information and other things. Really,
that's really a good comment for us, sir. Really, thanks a lot for us. That means a lot.
I am getting some projects done from my students on this.
All
so
right.
I got to know the details very well now. So it's really good for us to learn.
Yeah. That's so sweet of you, sir. Thank you.
Please
Thank you,
organize
Krishna,
like
sir.
this, ma'am. We'll be happy to even sit after 7 o'clock also.
That's so sweet. Thank you, sir. We will. We are there here to organize all this type of
In
FDPs.
fact, I never miss, madam. Other sessions, normally I used to miss AICT FDP also, but here I didn't miss.
Oh, that's so committed,
Even
sir.
after our
Thank
online
you.
classes and all, I used to come and sit.
Thank you, sir. Thank you.
One request, ma'am, please share
Yeah.
the materials through mail or something, ma'am. That would be good.
Yes, sir. We
Refresh
will, sir.
ourselves.
In your registered mails and in Telegram, all the groups will send, sir. Will send.
Yes.
Thanks.
Thank you so much, ma'am. Srinivas, sir,
Thank
everybody,
you.
thank you so much, sir.
Thank you, sir. Thank you.
And also, I would like to request, like, we have subscribed to your YouTube channel, ma'am. It's
Okay, Aditya,
Varangal
sir.
channel. And I
Okay,
request
sir.
not to delete any of the videos of these 5 days. I think it
No,
should be
sir,
long
not at all.
lasting videos. But in
Yeah,
future
sure,
also,
sure.
it would be like a reference for us.
Yes, sir.
Thank you. And we are sharing
Yeah,
the same
thank you.
videos with our colleagues and friends who
Oh,
are
that's
actually interested in this.
that's a great thing that you are doing for us, sir. Thank you.
Thank you.
Thank you, Aditya.
Harika here.
Yes, Harika, ma'am.
Actually, all these 5 days, a wonderful session, ma'am. Actually, I am the old passed out student from Balaji Institute of Science and Technology.
Is it? Yeah.
2006 passed out. Actually,
Oh my God.
Madam, please,
yeah,
please switch on your video, please. You are the alumni of BITS, so please switch on.
Hello, sir. Yeah, good evening, sir. Actually, these 5 days previously we don't have all these workshops and everything. 2006 passed out.
Okay.
So actually, we got a wonderful information. All these 5 days workshop. I'm doing my PhD from Satyabama Institute of Science and Technology, Chennai.
Okay.
So actually, I got a wonderful information from machine learning, and I got some of the. I'm having the doubts. Whatever the doubts, it was totally cleared. Really, it was a wonderful 5-day session. Really great, ma'am.
So
Very
sweet
much
of you,
thanks.
Harika. Thank you. Thank you.
I really thanks all of the management and each and everyone for this wonderful session, and all the session holders and who have taken their sessions. Really very great, ma'am.
Thank you, Harika. Thank you.
Thank you, ma'am. Thank you.
Still, any of the participants would like to share your feelings?
Hello, can you hear me?
Yes, ma'am. At your end, some disturbance is there, ma'am, from starting onwards.
Okay.
Yeah, yeah. Now it's okay, ma'am. You can, please.
Hello, can I now can you hear me, ma'am?
Sorry
Yes.
to say, ma'am, but
Can you hear me?
yes, ma'am. I can hear you, but
Yes.
some disturbance is there, ma'am.
Now can you hear me?
Yes, ma'am. Yes, ma'am. You can, ma'am.
Yes.
Please on your video and you can proceed, ma'am.
Disturbance. Hello. It was very good program.
Thank you, ma'am.
Madam, can I give the feedback?
Madam, 1 minute. Vishnu sir is cam. Vishnu sir Raju.
Yes, sir.
Madam.
Yes, sir. Arun sir.
Chief guest has come.
Yes, sir.
Hello, can you hear me, ma'am?
Dr. Vishwanath Raju.
Can you hear me?
Chief guest.
Yes, sir. Srinivas sir, shall we start the valedictory session?
Madam, 1 minute, sir.
Yeah,
I'm waiting
okay,
for sir.
Yeah, okay, sir. Okay.
Hi, ma'am.
Yeah.
Hi, ma'am. Yeah, ma'am.
Hello.
Ma'am, it was very wonderful session, ma'am.
Um,
Ma'am, my net disconnect 5 minutes before, ma'am. So I first question only I attended. Please, ma'am, again, can you send me the quiz link, ma'am?
Yeah, ma'am. Again, at last, we'll send all the links, ma'am. No
Okay,
issues.
ma'am.
Yeah.
Okay,
Don't
ma'am.
worry.
Thank you, ma'am. Thank you very
Okay.
much, ma'am. Okay.
Thank you.
Hello.
Hello.
Am I
Yes,
audible?
ma'am. Yes, ma'am.
Am I audible? Can I share my experience?
Yes, ma'am, you can.
Actually, I would like to say that it was really an enriching experience. And thank you for providing such informative and interesting session. And I suppose each and every slide or PPT was too informative and very well structured. So my big thanks to all the organizers and congratulations to whole team. Thank you so much.
Thank you, Babita ma'am. Thank you so much.
Hello.
Yes,
Jaya
sir.
madam.
Yes, sir.
Sir will join after a few minutes. You
Yes.
can.
We'll start the valedictory session.
Yes.
Yes. Yes, I delightfully welcome you all for today's valedictory session of 5-day online faculty development program organized by Computer Science and Engineering of Balaji Institute of Technology and Science. I feel it an honor to invite Dr. A. Rajendra Prasad Reddy Sir, Chairman of Balaji Group of Institutions, Dr. G. Rajeshwar Reddy Sir, Balaji Group of Institutions, Principal of our institution, Dr. V.S. Hariharan Sir, Convener, Head of the Department, Mr. Fasih Ahmad Parvez Sir, Coordinator of this 5-day FDP, Dr. Kandi Srinivas Sir, Co-Coordinator Nagaraju Sir, and CSI Student Branch, Dr. A. Arun Kumar Sir, teaching and non-teaching staff and participants to this valedictory session. So now I request our coordinator, Dr. Kandi Srinivas Sir, to speak few words regarding this online FDP program. Over to you, sir.
Thank you, madam. I, Dr. Kandi Srinivas, coordinator of this program. First of all, Honorable Chairman, Balaji Group of Institutions, Dr. A. Rajendra Prasad Reddy Garu, respected Secretary, Balaji Group of Institutions, Dr. G. Rajeshwar Reddy Garu, beloved Principal, Dr. V.S. Hariharan Sir, Head of CSE Department and Program Coordinator, Mr. Fasih Ahmad Parvez Sir, Co-Coordinator, P. Nagaraju, all the HODs, staff, and my dear fellow participants, good evening. I'm really very much delighted for giving this opportunity to share my views on this international 5-day online faculty development program with you. I feel I am fortunate to be as a coordinator for this faculty development program. At first, I would like to thank all the participants who have attended to all the sessions with enthusiasm and with tremendous interest. I hope you all have enjoyed all the technical sessions which were presented by eminent speakers. All the sessions are informative and enlightened. Nearly 1,200 members have registered for this FDP from different states and countries.
Okay.
Almost all have made their participation in all the sessions, and nearly 3,500 are watched our session videos. We used Zoom app platform for all these sessions. We also made all the sessions live in YouTube. First today, Professor M. Surendra Prasad Babu, Regional Vice President, CSI Region 5, delivered the session on the topic Big Data in Data Science. Second session, Dr. B. Satish Kumar, Professor, Department of CSE, JNTUH, College of Engineering, Jagityal, delivered the session on the topic Data Science Concepts. Second day, Dr. Shishikala Mata, Assistant Professor, Department of CSE, SR University, Warangal, was the resource person, and she delivered a session on the topic Deep Learning. The third day, Dr. Vikas Kumar, Assistant Professor, Department of Data Science, Central University of Rajasthan, has presented a session on the topic entitled Recommended System. On the same day, second session, Mr. Hemant Kumar, Assistant Professor and Certified Data Scientist, Department of CSE, Vidyavardhaka College of Engineering, Mysore, Karnataka, has presented a session on the topic entitled Machine Learning. And fourth day, Mr. Hemant Kumar, Vidyavardhaka College of Engineering, continue with the machine learning and algorithms. Today, that is the fifth day, Dr. Venkateshwar Rao, Assistant Professor, Department of CSE, NIT Warangal, has presented the topic effectively on neural networks and natural language processing. My heartfelt thanks to all the speakers for accepting our invitation and being as a resource person. I owe my gratitude to Chairman of Balaji Group of Institutions, Dr. A. Rajendra Prasad Reddy Sir, Secretary of Balaji Group of Institutions, Dr. G. Rajeshwar Reddy Sir, and Principal of Balaji Institute of Technology and Science, Dr. V.S. Hariharan Sir, for their encouragement and guidance they have extended to all of us. I sincerely thank Convener of FDP, Mr. Fasih Ahmad Parvez, and all my faculty friends for their support they had given in all aspects in making this online FDP a grand success. Finally, once again, I express my heartful gratitude to all the participants. Thank you, one and all. Over to Jaya Madam.
Thank you, Srinivas sir. Now I request the coordinator Nagaraju sir to speak few words. Over to you, sir.
Thank you, madam. So I P Nagaraju. I am the co-coordinator of this program, FDP program. So honorable chairmen sir, secretary sir, and HOD, principal, and all the faculty members, and all the participants. Very good evening to all. So first of all, I would like to thank Honorable Chairman Sir, Secretary Sir, Principal Sir for giving this opportunity to organize this program. So I would like to thank our resource persons, those who are effectively presented deliver the lectures on data science and new technology. So finally, I am going to express my gratitude to our beloved participants who are attended throughout the world, like so many countries like Oman, Philippines, and some other countries, and from the India also. So thank you one and all for attending this FDP program. Thank you all. Okay, over to you.
Thank you, Nagaraj sir. Now I request convener of the program and head of the department, Mr. Fasih Ahmed Parvez sir, to address the audience. Over to you, sir.
So, respected Chairman sir, Secretary sir, Principal sir, and program of this FDP, Dr. K. Srinivas sir, and co-coordinator Nagaraj sir, and all the technical team, Shravan sir, Ashish, Ramakant, Ranjit sir, and all other people who are behind this particular program, Jairam. So if I'm missing some names, please excuse me in this regard. And I'm really thankful to the management for giving this opportunity of conducting a program on data science. Of course, it was really a peak time for us to conduct this program, as the class work is going on in almost every university. So in this regard, I'm really thankful to all the participants who, even though with their busy schedule by taking the classes or labs, still they have attended this session, all the sessions regularly. And I would like to thank all the resource persons, right from Dr. B. Satish Kumar sir, Dr. Shashikala Martha, Mr. Hemant Kumar, Dr. Vikas Kumar sir, and Dr. K. Venkateshwar Rao sir, who have been really the best. They have presented the data science in a best way. And even I have seen the feedback that was been given by the faculty from different streams, from different parts of country as well as outside the country. So what I feel is that if this kind of FDPs we try to attend, then it will be more helpful to the society. And there are so many things that can be solved by using such kind of problems or such kind of technologies. And I really once again thank all my department faculty as well as the principal sir and all the core team members for making this FDP a grand successful. And a special thanks to Jaya for her beautiful anchoring. Thank you. Over to Jaya.
Thank you, sir. Thank you so much. Now I request our principal, sir, Dr. V.S. Hariharan, to address the audience, sir. Over to you, sir.
So very good evening to one and all.
Good evening.
Honorable Chairman of Balaji Group of Institutions, Dr. A. Rajendra Prasad Reddy Garu, and respected Secretary, Dr. G. Rajesh Reddy Garu, and Chief Guest of today's valedictory function, Dr. S. Vishwanath Raju, Vice Principal of JNTU Jagityal, and convener of these 5 days workshop, Mr. Fasih Ahmed Parvez, coordinator, Dr. K. Srinivas, co-coordinator, Mr. P. Nagaraju, and a CSI student chapter counselor, Dr. A. Arun Kumar, other faculty members, and my dear participants. It is a great honor for the Department of CSE to conduct this FDP program at a right moment. So where this data science is one of the emerging areas where it involves many aspects of the emerging areas like AI, ML, cloud computing, etc. So I hope all the participants might have utilized this opportunity. And another thing is also, as all the programs are live in the YouTube, so the recorded version will be always available for you as well as for the benefit of students. And also it's a great honor for us to have the resource person speakers from reputed organization having experience in their area of specialization. So whatever they dealt last 5 days. So really we are very much thankful to all the resource persons from different institutes. And finally, I would like to thank all the participants for your patience listening in all these 5 days. And also thank Department of CSE for coming out with this very useful workshop at this juncture, FDP at this juncture. Thank you once again. Over to Mrs. Jayashree.
Thank you, Principal Sir. Thank you so much. Now, before inviting our today's chief guest, Dr. S. Vishwanatha Rajugaru, I feel it an honor to introduce you, sir. Sir is Professor, Vice Principal, JNTU College of Engineering, Jagityal. Sir, working as Professor of Computer Science and Engineering, he has more than 23 years of experience in teaching, research, and administration. He awarded his PhD from Acharya Nagarjuna University, Guntur. Sir certified CMI in Education, Leadership, and Program Management from Dewey College, London, which is sponsored by MHRD AICTE. Sir has been honored with Best Computer Science Engineering Award for ISTE AP for the year 2014 and Best Citizen of India. His research and area interests include programming methodologies, algorithms, information retrieval, biometrics, databases, data mining, etc. He filed 11 Indian patents deriving from his research. His research contributions are not only confined to his subject area, but also extend to other related domains arising out of the new education system, assessment and accreditation as their impact on Indian higher education. So to add impact to his academic credentials, he has undergone training as well as speaker for the quality improvement in education at NITTTR, WOSA 2012 and 2014, TCS, Infosys, NBA, and NAC. Sir supervised 9 PhDs and 4 PhD scholars are under process. Sir published 80 research papers in reputed international and national journals and conferences. He has authored 4 books and implementing 2 AICTE-sponsored research projects and one fellowship from TS and ST. Sir has been a member for several governmental committees. He delivered number of invited talks, expert lectures, and keynote address on various technical topics, as well as outcome-based education, NBA, NAC accreditation process in the country and outside India also. So, Sir has organized several workshops, seminars, and conferences. Sir has visited Singapore and Taiwan and interacted with several academicians and researchers. Now, I request Dr. Vishwanatha, sir, to address the participants. Over to you, sir.
Yeah, thank you very much, madam, for sharing my experience.
Thank you, sir.
I would like to include in that one more point, madam. Recently,
yes, sir.
I have selected for the Telangana State Best Teacher Award for the year of 2020.
Oh, nice.
The government
Okay,
of
sir.
Telangana. Okay.
Congratulations,
nice,
sir.
Yeah, thank you. So, Good evening to all of you, my dear participants and organizing committee members. Respected to Chairman Rajendra Prasad Reddy Garu and Secretary Rajeshwar Reddy Garu, Principal V.S. Hariharan Garu, and convener of this program, Parviz, coordinator and co-coordinator K. Srinivas and Nagaraju, organizing committee members and participants, college management, faculty, staff, HODs, and finally, not least, all the resource persons. I might be received the information from the different participants, what they have given the feedback. By that, I analyzed it. Okay, all the resource persons gave excellent, informative, and also useful information for the society as well as community. It is honor and a great pleasure to be with you to share this important occasion with you. That is what I must congratulate to all the organizing committee members who supported directly or indirectly for successful completion of this event. So this is what, once again, I'm saying the congratulations to all the members. Now I would like to share regarding the data science program. Data science is an interdisciplinary area. That is what we are, I think we know, all, you might be received from the different resource persons. It is why it is interdisciplinary area means it is a combination of multiple domains like mathematics, statistics, machine learning, artificial intelligence, etc. So it is a interdisciplinary area. When it is interdisciplinary area, then what is the major role of the data science means? As per my observation, generally the data could be available in the form of structured and unstructured. You know, the data is in general, structured means it is a table format. I'm giving a simple example. Unstructured means it is not available in the form of table, like a letter format. Okay, that may be coming to the structure, that is different, but I'm talking about the data structure. Okay, so whether it is available in the form of structured or unstructured, but now the data is available in the various places. But now what I want, if I want such certain information that I should able to extract from either format, either format means either structured or unstructured. So there I should apply the certain mechanism for extraction of the information which I require from the either format. So that is what I think you might be received from the resource persons. Suppose data table format, if I want, I can extract which I want exactly. Suppose the data is available in the form of unstructured, which I want that I should extract approximately, not exactly. That is the basic difference between the structured and unstructured. So you might be learned many algorithms regarding the data extraction from the unstructured data. And I would like to share one more point in this. There are hundreds of applications are there. Data science, when it is an interdisciplinary area, you see the definition itself, it is saying interdisciplinary area. Then it is having hundreds of applications. So wherever you see that, you can use the data science concept. Suppose if you want to predict about your friend, how he is going to behave in the next minute. This is also I can predict based on the past 30 days information, or maybe past 3 years information, or past 4 years information. So there I can apply the data science concepts also. Or maybe how my principal going to behave me if I'm going to meet with him tomorrow, maybe day after tomorrow. That is also I can predict by the help of the data science concepts only. So these are the things I may be going to get it in the future. You see that tomorrow you can see the certain apps. So suppose if you install that app before entering into the principal room or HOD room, you can predict that app may be giving certain solution. So how he is going to act in front of you, how you want to respond for that. Such a solutions also you may find in the future. We can see that such a information. So that is what the next generation, I think. And also I would like to share one of the point is, I said mathematics, machine learning, algorithms, etc. The machine learning, I think it's a part of the data science only. machine learning concepts are supervised learning, unsupervised learning, reinforcement learning. So supervised, unsupervised, reinforcement. Just I give briefly regarding the supervised, unsupervised reinforcement. Supervised means where the labelings are there, then immediately I could able to find, I could able to access it. Suppose if I enter into the campus, arrow marks is not there in the campus. That means what? It is unsupervised concept only. I should apply the unsupervised concept. If the arrow marks are there in the campus, then by the arrow marks, I can reach my place easily where I want to go. Suppose if I want to go to the CSC block or maybe electronics block or maybe electrical block, it's like you see that there is a labeling. The arrow marks are nothing but labeling. If the labeling is not there, how you feel? You feel in uncomfortable way. So that what we want to do, labeling concept, where the labeling data is there, there I should apply the supervised learning. Where the labeling concept is not there or labeling is not there, in that case I have to be apply the unsupervised learning concept. And the third one is a reinforcement learning. Reinforcement learning, this is not new. As per my analysis, we all applied knowingly or unknowingly reinforcement learning. When baby birth, when baby is small, okay, maybe 3 months or maybe 8 months or 10 months, what kind of mechanism they used to apply for their standing, for their running, for their walking? That is what they used to apply, the trial and error method. So trial and error method means when they try to stand, then immediately mother will instruct, mother will observe, mother will direct. So such a concept is nothing but reinforcement learning only. So everybody has such that experience. So reinforcement, I think in the childhood, we all applied knowingly or unknowingly. So this is what the concept of the supervised learning, unsupervised learning, and reinforcement learning. The next point, last point is I would like to share with you. Our government of India, Honorable Prime Minister, he has been introduced a new program that is AI, artificial intelligence, for what? Social transformation, inclusion, and empowerment. So from last 3 days, I think maybe they are organizing several sessions. Maybe another 3-4 days will be there. So that they are taking very seriously. In the next generation, AI is going to play the 100% role in our community. So this is what my conclusion. So at last, based on the participants' feedback, so the session was excellent. I heard from 3-4 participants before, okay, coming to this play. So in that aspect, you organized in a well manner. So like this, I hope I want to see in a future. Thank you, one and all, for giving this opportunity. Thank you.
Thank you so much, sir, for your valuable words. Thank you, sir. Thank you. Now it's time to issue the certificate through online. Our coordinator has planned to present the certificates to the resource persons, organizer, and few attendees in the presence of chief guest, chairman, and principal. You will receive the certificates within couple of minutes. Srinivas, sir, you can please forward it.
Okay, madam.
Yeah. Yeah, I hope it is done. Thank you. We have international participants for our FTP program. I request any of the international participants who would like to share a few words with us. Before Ranjan, sir. Jennifer, ma'am. Okay, thank you.
Hello.
Still anybody? Yes, sir.
Hello. Madam.
Yes, sir.
Jennifer, madam has sent one voice message. Please,
okay.
The technical team can play the feedback.
Okay. Okay.
Nagaraj sir.
Okay, sir. Still, any of the participants
Nagaraj
would
sir.
like to share? Okay. Okay. Thank you. Now, I deem it's a privilege to propose vote of thanks. I firstly like to take an opportunity to thank Chairman Dr. A. Rajendra Prasad Reddy sir and Principal Dr. V. S. Hariharan sir for the perfect logistic support and guidance they've extended to all of us. I also extend my sincere thanks to convener, head of the department, Mr. Fasih Ahmed Parvez, for his enormous effort he had put in organizing for this session. Thank you, sir. My deep sense of gratitude to Chief Administrative Officer, Mr. S. Suresh, sir, and all the heads of the department for the advice given by them time to time. And my deep sense of appreciation to the coordinator, Dr. Srinivas sir, and co-coordinator Nagaraju sir, CSI student branch, Dr. Arun Kumar sir, teaching and non-teaching staff. And ladies and gentlemen, I owe my gratitude to all the resource persons who made their presence and enlightened us in all these sessions, Dr. Prasad Babu sir, Dr. Satish Kumar sir, Dr. Sashikala ma'am, Dr. Vikas sir, Mr. Hemant Kumar sir, Dr. Venkateshwar Rao sir. Thank you, everyone. I express my gratitude to all the faculty and special thanks to all the participants across the globe who were with us for this 1 week FTP program. Thank you everyone for your cooperation. I thank each and everyone who made their part in this making this program successful. Thank you all. We'll provide the feedback link in the YouTube and the chat box and in the Telegram group. Thank you all. Take care. Signing off. Jai Shri. Over to you, Srinivas sir.
Madam. Hello.
Yes, sir.
Nagaraj sir.
Okay, sir. Okay. Now I am ready.
Just you, please. 1 second, madam.
Okay, sir.
Nagaraj sir. Okay. Finally, thank you one and all for participating in valedictory ceremony of International Faculty Development Program, and we need your cooperation and your support in conducting this type of programs in future. Thank you very much. Over to Jaya madam.
Thank you, sir. We can end the session now.
Okay. Nagaraj sir, you can end the session. All of you, please fill the feedback form and quiz as early as possible, because within half an hour we are going to close the quiz and feedback. Thank you.